single spike, one single frequency there of gamma ray energy rather, that is emitted by potassium. Uranium's more complicated, thorium's more complicated. Okay? But these are the emission spectra that are being recorded by the gamma ray logging tool. And you have two basic types of gamma ray log. One a bit more simple, one a bit more complex. These are how gamma ray logs are displayed. So what you're going to see, I'm going to show you for each logging type, we're going to see this kind of display. What do you think this is? What do you think you're looking at here? This is actually the top of a log data sheet, right? So these are actually, now, this is all done electronically, okay? So the data is recorded, processed, it's all done electronically. It arrives on the petroleum geologist's workstation, and then she or he works on it using some software like Petrel or whatever it is that they're using, okay? But prior to probably about 10, 15, 20 years ago now, everything was done on paper, and this is what the paper copies would look like. And in fact, this format is carried through even to the electronic formats. This is what you would see in Petrel if you were using that tool to display log data. But these are actually pictures from the original paper copies. So what you have here is, here's the actual log. So we've got depth on the y-axis, same here. You've got the scale of your gamma ray log is here, so a minimum to a maximum. API stands for American Petroleum Institute. These are the units for a gamma ray log. Most log data is actually calibrated against some known bit of rock or mineral, right? It's calibrated. So the units are relative to that calibration. So 0% would mean that it's 0% of the calibrated gamma ray emissions from a particular specimen. 100% would mean obviously 100%. If you were getting more emissions than the standard calibration, it's going to be 120, 140 and so on. Okay, and you can look up details of those calibrations. But this is a standard gamma ray log. It's reading about 70 American Petroleum Institute units of gamma ray emissions. Okay? What do you think a spectral gamma ray log is? What do you think that means? In fact, look at this one and it basically tells you. We just said, didn't we, that potassium, uranium and thorium all emit gamma rays in a particular way. So this is the gamma ray signal being recorded by a tool but broken down into the different emissions. How do you think that is done? It's because they have different emission spectra, what I just showed you. Okay. Why might you prefer spectral gamma ray data to standard bulk gamma ray data, if you like? What advantage does this have? Based on that previous slide, what advantage would spectral gamma ray data have? What could you do with spectral gamma ray data that you could not do if everything was just a whole gamma ray signal average?
Find out what rock is
Yeah, well, yes, to some degree. What minerals, at least? Shale is a rock, I know, but that really needs clay minerals. You can basically see the composition of what is giving you that gamma ray signal. Which of those is particularly interesting?
Uranium.
Organic matter. So a uranium gamma ray spectra is great for source rock identification, for example. Okay? Bulk gamma ray will give you a hint that there's a source rock present, but it won't give you the definitive measure of organic matter that the uranium signal will give you. Okay, so spectral gamma ray is better typically than bulk gamma ray. That's actually a proper term. Here's what the gamma ray response looks like. If you want to learn one thing from this lecture, these diagrams are the thing to look at. right? Because they're a really nice summary. And all of this is taken from Ryder 2002, which is basically a book all about well logging. If you just look it up on Google, if you're interested, definitely worth getting a copy. You don't need it for the course, but you can also look up in Blois and Swarbrick has got quite a lot of material about this. So here we have a vertical succession, which have a series of different lithologies like compact sandstone, porous sandstone, limestone, micaceous sandstone, various different types of shale, and so on. Here's the gamma ray log response. This isn't spectral gamma ray, it's just single gamma ray. And what do you see? You see that basically shale gives you a high gamma ray value relative to sandstone, which gives you a low gamma ray value. Does it make any difference whether the sandstone is compacted or porous to the gamma ray response? No. Gamma ray tells you nothing directly about porosity, but it does do a very, very nice job distinguishing between shale and sandstone. Now, if I were you, I would make sure that I understood very well gamma ray logs and this kind of response to the stratigraphy before you went into your exam, I'm just saying. So, yeah, that always gets your attention. I'm going to write that down. So gamma ray logs are a lithology indicator, but not unique. What does that mean? Can you see an example on that response that is non-unique? Do you understand what I mean by non-unique?
Clay and shale.
Sorry?
Clay and shale.
Clay and shale. Yeah,
That's
but
the
I mean, they're fine-grained dirt, aren't they? They're not so different anyway. But yeah, you're right, clay and shale. But there's something a bit more striking.
Sandstones.
Which one? This sandstone is lower than most of the others, isn't it?
Mm-hmm.
But if you look at that clay or shale, those clay lithologies there, they're actually quite similar to Arcos. Who can tell me what Arcos is?
Is that sandstone rich in feldspar?
Right, sandstone rich in feldspar, hence the X. So an arcosic sandstone gives you a very similar signal, and a micaceous sandstone actually even more so, gives you a very similar signal to a kaolinite rich mudstone or shale. Right? So gamma ray logs are not unique. Clean quartz rich sandstone gives you a nice low gamma ray value, as does limestone, but more micaceous sandstones, so texturally, petrographically less mature, compositionally less mature sandstones will give you something that's much harder to distinguish from mudstone. Where have you all seen a compositionally very immature sand on a field trip? I was with you. Since we've only really been on 2 field trips. Do you remember the pit in the woods near the reservoir at Burrow Tor, where the granite was being broken down by hydrolysis? Do you remember that? The sand that was coming out of that granite, at that point that's what it was sand. That would have been very rich in minerals, in mica. It would have been a micaceous sandstone. It would have given you a higher gamma ray. Any questions about this? It's important you understand it. One final thing: if the amount of shale in the sandstone changes through that sandstone, you might get a log motif like this. Right? Do you all see that? So it's not vertical, basically. Okay. You need to remember that because you will be doing an exercise on that in a couple of weeks. Okay? Good. Any questions about this slide? It's an important one. There must be something going on in that corner because you two are doing spectacular yawns. If there are any flies in the room, you would have eaten them by now. Any questions about this? No? Sure? All clear? Good. So here's an example that sometimes do as an exercise. We're not going to do that today. Here's a series of well logs displayed in Petrel. This is a screenshot from Petrel, so standard well log interpretation software. You may not be able to see it that well, but this says base chalk, this says Cretaceous, this says Kimmeridge clay, this says base lias, I think. So these are stratigraphic horizons that are identified in this well. Formation tops and correlation. If you correlate these well logs, what it would mean is identifying the base chalk in all these different well logs and then joining it up as a horizon. That would be the process of formation top, identification, and correlation. Okay? You can do that based, I think these are probably a gamma ray log and something else. I don't know what the other thing is. Okay, so this is a key use of logs. Gamma ray logs are particularly good for formation top ID because they give you the basic distinction between shale, sandstone, limestone, maybe one or two other lithologies. Right? They're a very good summary log. So let's move on to sonic logs. Now then, what this diagram is showing you is the borehole, right? The borehole walls. There's the logging tool being lowered down, or probably pulled back up the borehole, right? And what you have in each of these logging tools, these are active sensors. So what you have is transmitters, T1, T2, they basically emit sound pings. They're like sonar on a submarine, right? Ping, ping. And the sound signal comes out, travels through the rock, and gets recorded at receivers 2, 3, 4, and so on. Basically, there's an array of receivers. And how do you think then, from the transmitter to the receiver, how do you think that receiver works out the velocity, the sonic velocity of the log?
Vibrations.
Sorry?
It's vibrations.
The sound vibrations, yeah, sound signal is sent out. But what does the logging tool actually measure? Speed. Right, it takes the time. Well, but hang on, how does it measure speed? It can't measure speed directly. What does it actually measure? Time. Record, this sends out a ping, that waits to see how long it takes before it hears that sound signal hit that receiver. And that's why you've got an array of receivers here, because you can measure the slightly different arrival times for those pings. And from that, you can reconstruct what we call the interval velocity. The velocity of the interval between the transmitter and the receiver. Why might this be a little bit more complicated than it first looks? What's in the borehole? Fluids, probably, right? So some of this sound energy is not travelling through the walls of the borehole, it's travelling between the borehole wall and the receiver, either through air or through fluid, right? So you have to make some corrections for this. The diagram on the right is showing you a more sophisticated setup which uses tools which have different receiver-transmitter spacings. Okay? I said to you petrophysics was a bit dull. Petrophysicists will spend lots of time analysing the kind of data that comes from these different receiver-transmitter spacings in order to get better, higher quality interval transit time data. Why do you think interval transit time sonic log data is so important? Why is it one of the most useful logging tools?
Is it because it varies from different lithologies, so you can...
It certainly does, but not really. Gamma ray is probably better at identifying lithologies, but what? Go on.
Tells you about fluids.
There aren't many liquids down here, but there will be solids full of liquids. Yes, but not uniquely, most likely. No? You think out the box a little bit here.
Does it help you like correlate with seismic velocities?
Exactly, very good. It's all about seismic. Remember, seismic data is our other main source for subsurface evaluation, isn't it, right? So this takes direct measurements of the interval velocities of the rocks in the wellbore. You can then use that to help understand your seismic data, because what we never know about seismic data, or what we need to know, we've got seismic data in two-way travel time. What do we need to know? What do we need to do? Convert that two-way travel time to
Depth.
How do we do that?
Velocity.
Velocity. What is this tool giving you?
Velocity.
Velocity. Right? That's the link. So the sonic tool is key. Here it is, a little bit dull really as logs go. There's your sonic log, there's your velocities, there's your microseconds per foot of all units. Lots of logs are still in imperial units just because of dominance of America in the hydrocarbons industry, I suppose. Okay, and well, integrated travel time, I don't really need to worry about that. But these logs are pretty easy to read compared to some others. And usually there's some information about the transmitter-receiver setup. If you're a petrophysicist, you can use that T3R1 2R². Sounds like a droid from Star Wars, doesn't it, actually? You can use that to gauge the quality and problems that there might be with the data, right? So here's an interesting example. The caliper log, let me just explain that to you. Caliper logs, you know I said that the walls of the borehole can often be quite irregular. It's not like a perfectly smooth, uniform diameter all the way down, simply because drilling is quite messy, right? And different rock types respond differently to being cut by a drill. So the caliper log is basically telling you the diameter of the borehole at any position down the borehole in, I think this is inches. So we have 11 inches, 16 inches. So it's quite irregular. There's a variation of what's about that much in the width of the borehole as you go down. So it's, you know, it would be like this, that kind of irregular shape. Okay? Got 25 meters on the y-axis. So you can see some changes in the width, the diameter of the borehole. Why might that be of relevance to the sonic log?
Because it gives a
Yeah.
curve.
The sonic log's going to give you,
A lower reading.
yeah, it's going to, yeah. The interval transit time, would that be more or less if the sonic signal is travelling for the most part through air? Air has got a higher or lower velocity than rock. Lower. Right? Basically, sound travels faster through solids than it does through liquids and gases. Right? So the interval transit time is going to be substantially higher when you've got the sound travelling for further distance through air. Can you see, therefore, why these peaks in interval transit time, which of course are the inverse of velocity, right? Transit time is opposite to velocity. Those peaks in interval transit time correspond to points where the borehole is much wider. Okay? If you were to try and calculate seismic response based on this data in its form, you would get it completely wrong. What you would be seeing or measuring is basically the state of the borehole, not the velocity of the lithologies in the borehole walls. So this caliper log is often used in conjunction with the sonic log in order to correct the sonic data. And usually by the time you see this kind of sonic data, it will have been cleaned up. The people who collected the data would have fixed these problems. Okay? So that's caliper logs. Any questions about that? Sonic logs then, typical responses. So look what we've got here. We've basically got high, or rather high, yeah, well, this is interval transit time, remember, so it's the inverse of velocity. So you've got lower interval transit times for lithologies like sandstone and limestone, higher interval transit times for shale. So which of those two has got the higher velocity? Which is faster in terms of velocity then? Compact limestone or shale? limestone is higher velocity, generally because it's harder. Shale is often quite soft rock. You know, I think I said to you a little while ago in a previous lecture, imagine a lump of shale and a lump of limestone, hitting them with your hammer. The lump of shale will be a dull thud. The limestone will be a big ringing noise. I don't know if it's all words
See,
you use.
it's more
One,
like that.
maybe. Okay. Velocity of limestone is higher. So that's what the log is basically showing you. What has the what are the two lowest velocity points on that plot? What pathologies? Coal, yeah, coal's pretty low velocity. What else? What is distinctive about the part of the shale that is low velocity?
Less compacted.
It's not compacted. So it's basically goo sitting on the seafloor, contains lots of pore space, lots of water, therefore has very low seismic velocity, low sonic velocity. Okay? So if you look at a velocity profile down from the seabed, it will increase quite quickly, because you go from unconsolidated mud that you could be up to here in if you tried to walk in it, to basically rock. And that happens over the space of a few tens of meters. This all clear? Good. The other thing that you can get then from the sonic log basically is porosity, because compact shale, what do we mean by compact? We mean it has lower. What gets lost when a rock gets compacted or sediment gets compacted? We'll talk more about this in a couple of weeks. What goes? What's reduced? Porosity. Because basically you squeeze the rock, the spaces between the grains get smaller and smaller, so you reduce porosity, right? So there's here a direct relationship between velocity and the degree of compactedness of the shale, which is basically a porosity effect. Alright? So we can look at that in a slightly different way. Here is a cross plot showing interval velocity versus porosity measured from core as a percentage. So we've got a range of porosities from 2 to 20%, and you can see that you can fit a linear best fit line through this cloud of data, which basically then gives you a relationship between sonic velocity and porosity. So if you can measure from your sonic tool the interval transit time, the velocity, you can actually calculate porosity. So porosity phi equals this. Okay? So this is the transit time formation water minus the transit time of the rock matrix divided by the transit time from the log minus the transit time from the rock matrix. So you need to actually know what rock type you're in to do this calculation. But that's basically the formula that you can use derived from this best fit relationship. So I told you that there were lots of graphs. We are now in graph land. This is what petrophysicists do. This is why I always thought it was a little bit dull, because I like big spectacular seismic sections that show you crustal scale action, not the porosity of a dolomite. Is it 12% or 13.5%? Right? That doesn't do it for me. But some people, thankfully, find it really interesting, because in the end, how much oil and gas you get out requires this kind of detailed analysis. So here's the same basic graph, but now with much more information on it. You have these lines for different lithologies: sandstone, limestone, dolomite. So we're plotting porosity against interval transit time. And you can see that it's a non-linear relationship. So in other words, the relationship between sandstone, porosity, and interval transit time is somewhat non-linear. It's not a straight line. But we know what the relationship is from lots of measurements that have been done in analysis. So this kind of plot is very useful. It means that you could say, I'm looking at the sonic signal from a sandstone unit. You could read off the interval transit time, and it'll give you a porosity value. Right? Why do you want to know the porosity of a sandstone? It's a basic reservoir property, isn't it? Okay. Is this effective porosity, do you think, or standard porosity? Standard. Remember, effective porosity is how the pores are joined together. What we're probably measuring here, well, maybe though, because surely a rock with isolated pores, 10% porosity, would give you a different velocity from a rock where the 10% of porosity were all connected. Right? It might make a difference to the velocity of the rock. So I would say probably somewhere between standard porosity and effective porosity. It's going to be somewhere, maybe closer to standard porosity. Do you all understand this plot? You could use it on a section of data like this. We're not going to do the exercise, but basically you could look at the sonic data, which is this, the interval transit time data, and you could calculate from that porosity of these different units, right? Using that graph that I just showed you. I'm not going to ask you to do it because you'll be here all afternoon, right? But you can go through this process. Here's some of the values that go into the equations. The formation water velocity, the matrix velocity. Remember I was just talking you through that equation? These are the values that you plug in. You read your interval transit time off the relevant bit of the log that you're interested in, plug in the numbers, you get a porosity value. Okay? Clear? Right. We've done gamma ray, we've mentioned calipers, we've done sonics, now we're on to neutron porosity and bulk density. So, bulk density is another active sensor. Instead of listening, that's the right word, for gamma rays coming from the rock, it basically bombards the rock with gamma rays from a radioactive source. So, the tool has essentially a radioactive emitter. It sends out then photons at gamma ray frequencies, and they basically hit electrons. The electrons then emit a photon and an electron. It's called Compton scattering. Anybody do A-level physics? Did you do Compton scattering? That's what happens. And the sensor in the neutron, in the bulk density tool rather, records probably the recorded electron, I think, I'm not sure. One of these two things it actually records coming back to the tool. And what do you think that might tell you? Measures the density of electrons in the medium that you're looking at, free electrons particularly. What do you think that might do? What's it going to be good for actually identifying? Let's have a look at the responses of a bulk density log. Based on that, what do you think it's good at telling you? Measuring the amount of electrons in something. What do you see on there where you've got the same lithology in slightly different forms and a slightly different density, bulk density response?
Doesn't tell you how saturated something is.
What units do what units as a petroleum geologist would you check out on that log first?
The porosity values that you have.
Right, porosity of what though? What of all the basically we've
The
got sandstone,
sandstone.
limestone. Right, let's focus on the sandstone because lots of reservoirs are sandstones. What do you see in terms of the different responses there from those different sandstones?
There's a higher porosity for the, I think is it lower density?
Not porosity. This is bulk density we're getting here, right?
It's 20%.
But the log is measuring
Look on
bulk
the right.
density. But if you look at the bulk density of the sandstone, a 10% porosity sandstone, it's what, 2.49 grams per centimetre cube. if you look at the bulk density of a sandstone that contains water and gas, it's lower, right? By at least a little bit. So this bulk density tool will actually measure for you, or will indicate hydrocarbon content when you compare a dry sandstone with a hydrocarbon containing sandstone. So that's one thing that bulk density does, which is pretty useful. It's not a spectacular difference, but the difference between that and that, particularly that and that, is enough that you may actually be able to identify oil and gas bearing sandstones using one of these logs.
So it doesn't give you
Hydrocarbons will be low.
And in other senses, it's not, I mean, the shale, the difference between compact and uncompact shale, you can see it spans pretty much the entire range of the sandstone and limestone ranges. So a bulk density log is not good on its own for discriminating lithology. What it's good for doing is if you can identify different sandstone intervals from, for example, your gamma ray log, you can then use the bulk density log to try and figure out what fluids those different sandstones contain. Right? Do you all understand that? You remember I said at the beginning of the lecture about integrating log data? This is now what we're getting on to. And the bulk density will also let you do a porosity calculation. Okay, that's the other way in which it's useful. I think you said that before. So basically, you make measurements of row B, which is essentially bulk density read off the log, bulk density of the matrix you need to know. You plug it in, you can get things like porosity. Not things like, you can get porosity. Okay, so bulk density logs, like sonic logs, are another way that you can actually get density values. But you need to know something about the lithology you're in. You can't do it blind. You need to do it integrated with other log data. So that's bulk density. Let's talk about neutron logs. Neutron logs, again, are an active sensor. They emit lots of neutrons. These bombard the rock, and essentially they interact with hydrogen atoms. So the amount of neutrons you get back to the sensor is controlled by the amount of hydrogen atoms there are in the rock. Okay? So the bulk density was measuring electrons, which is essentially directly proportional to the density of the rock. But here we're measuring the number of hydrogen atoms. Why might we be interested in the hydrogen atoms? This is all plotted relative to limestone. Remember I said the logs are calibrated? Plotted relative to limestone. Why might we be interested in hydrogen? Because we're looking for hydrocarbons. Hydro, hydrogen, right, absolutely. So hydrocarbons are going to contain lots of hydrogen atoms, aren't they? Okay?
This is the choice of matter, right?
So here's a neutron log, same format that we've been looking at. Look at the sandstone here versus the sandstone there. Right? Basically, lowish neutron return in a clean sandstone, in an empty sandstone or water bearing. Higher neutron effect when there's gas, oil, or actually even water. Yeah, sorry, this isn't water bearing, this is dry, with either 0 or 10% porosity. If it contains water, particularly if it contains gas, you'll get a different signal. Okay? Again, shale's very variable, not much else to say about that. Okay, so neutron porosity is a good way to actually indicate the presence, particularly of gas. Here's the display. Don't think we really need to go through that very much. It's the same sort of routine you've seen already. Caliper log, gamma ray log. We're starting to combine different log types now. So we've got density log, neutron porosity. I think that's
We don't do anything. Exactly to use it.
cable retention and so on. So we're starting to put together several logs into one display. Now then, remember I said a neutron log was calibrated against limestone. What that means is that neutron porosity and bulk density will give you pretty much the same result when you're looking at limestone, because the neutron porosity log has been calibrated to make it indicate the density of the limestone. Right? In effect, that's what has been done. So what you'll see is with the neutron log that in other lithologies you get a slightly different response, and you need to actually correct. Right? So in a sandstone you get separation between the neutron porosity and the bulk density logs. Okay? And the only place that you don't get that separation is in the limestone because of this calibration. So just bear with me a second. I'm going to get to the real point of this. What that means is, amongst other things, is that if you do a neutron porosity over a sandstone interval, you basically get a large negative separation between the bulk density and the neutron density logs. Where you see these two logs separated, assuming that it's a sandstone lithology, that is basically telling you that there is gas. That's what we call the gas effect. Right, so it's a pretty much direct indication of the presence of hydrocarbons. Okay? And you can see this is the line plotting core porosity against neutron porosity units, and the scatter that occurs in here is because of the presence of gas. It shifts you away from this line of relationship. Right? But the takeaway point from this is separation between bulk density and neutron gives you the presence of gas. And that means that you can actually cross-plot neutron versus bulk density on a thing like this, neutron porosity index plotted against bulk density logs. You find that lines up the graph corresponds to particular lithologies, so clean limestone, clean sandstone, and you can actually get then porosities. If you actually plot neutron porosity versus bulk density, and it's a sandstone unit you're plotting it in, you should get the point that lies along this line somewhere, and it should tell you whether you're dealing with a 40% porosity sand, which would be lovely, or a 5% porosity sand, which would be pretty rubbish. Okay? So that cross plot between bulk density and neutron density gives you porosity. So there's several things that you can do with these two logs together. And we're almost done now. We've got one more log to go. Here's just a final example. You can try this exercise if you like. We won't do it now. You've got the information that you need. We've got a sequence through the southern North Sea. The Rotliegend reservoirs are in here somewhere. So gamma ray is the green. Low gamma ray, these intervals. So Rotliegend is probably going to be one of these low gamma ray signals. You can look at these data. Look, can you see anywhere on there where the neutron density and bulk, the neutron log and the bulk density log are separated? Well, anyway, look, compare this back to what we've just been discussing. If you've got questions, we can discuss it again next week. You can try this exercise, basically, just an example from the trial log. And then one final log we need to deal with, resistivity. And this is again one of the oldest log types. It's been around since I think it may have been the first log type that was invented, the first type of logging tool that was run. And what a resistivity log does is it measures the resistance to the flow of electrical current. So basically, you put down the whole the resistivity tool generates an electric current and tries to get it flow from positive to negative in the tool, and it basically measures the resistance to that flow. Okay, just like resistivity. What do you call it? The tool that actually measures resistance. Basically measures the resistance, and that gives you things like porosity, tells you something about the nature of the pore fluid in the rock, and particularly tells you something about as well the presence of clay. Those are the things that the resistivity log distinguishes between. So how does it work? Well, you've got basically sends out an electrical current, right? 2 electrodes, transmitting, receiving, and one key thing is how far apart those 2 electrodes are. Why do you think that might matter? They're very close versus far apart. How might that affect what you get back?
If they're close, you'll get the radius of the readings will be shorter, whereas
Exactly. So if you've got your 2 electrodes, positive and negative, they're very close to each other. The electrical current doesn't go very far from either of those electrodes, so your depth of penetration is low. If they're further apart, like this far apart, then will probably penetrate quite a long way into the rock. Okay? So basically the separation of the electrodes is really key.
spend the rest of the week, month off.
Alright? And there are various different ways to deal with that, which are outlined on the slide there, which I won't go into. The basic principle is electrode separation matters. And most resistivity logging tools contain an array of different separations of electrodes. So they measure the resistivity at various depths into the formation block. And that's what these plots are basically showing you. It's basically distance away from the wellbore with resistivity plotted against distance. Okay? And that's the main thing to take away from that zone, that slide. Apart from, what do you think these terms mean? Flushed zone, invaded zone, uninvaded zone. What do you think they might be referring to? What is flushing or invading what? What's down? What has there been lots of down the well, or while it's been being drilled? Drilling mud. Yes, exactly. So what do you think might have been invading the rock in the sides of the well? Drilling mud. Right? Basically, the drilling mud is at pressure in the well. The pressure is maintained, isn't it, to keep any gases and things that come out of what's being drilled from escaping up. It controls the conditions at the bottom of the well. But the fact that it's mud at pressure means that it can force its way into the porosity that's present in the rock walls. So the flushed zone is basically that part of the wellbore that is just completely saturated with drilling mud. The invaded zone is where the drilling mud there's some present. The uninvaded zone is the part of the rock that has not seen any drilling mud. The drilling mud has not got that far into the rock. Okay? So the resistivity, if we wanted to know the actual resistivity of the rock formation, we would want this value, not this value. Right? So that's why depth of penetration in the resistivity log is so important. That's why you usually have different readings made available to you. And this is what a resistivity log looks like in terms of response. So there you can see we've got basically high resistivity in a tight limestone, tight meaning low porosity. We've got high resistivity in coal. We've got lower resistivity in things like shale. But very high resistivities in salt and hydrate, so evaporating rocks. Okay? Those are the lithological responses, pretty straightforward. Here's the point about zones of invasion again, the resistivity profile. So this is the wellbore in 3 dimensions. There's a mud cake, there's the flushed zone, a bit of the well that's just the well wall that's full of mud. A bit out here is virgin formation, it's called. Did you all understand that? here's another plot as well, which is a fluid mixing, so there's mud filtrate which declines to 0 proportion in the uninvaded zone. Okay. So pretty straightforward, but actually it means that you have to be careful about what you're seeing in your resistivity log. So here's a profile through a situation where you've got moving away from the well bore, right? So the well bore is here, the borehole is here, and as you move away from the well bore, in terms of proportion that's present, right? You are going from a zone where there is 100, well, not quite 100% mud filtrate because you've got some residual oil. The mud cannot force out all of the oil that may have been present, just most of it. And you go away from mud filtrate back to a situation where you've got some formation water and some oil. And this is the resistivity profile you get across that zone. So again, if you want to measure the resistivity that tells you what fluids are present, you want this, not that. Right? That's really all this slide is saying. And then we've got a series of other slides now that basically make the same point, showing different possible configurations of a reservoir rock. This one has got a mixture of formation water and oil. This one's got a bit more formation water. This one's all formation water, right? So these are going to have different resistivity profiles. Oil filtrate is a little bit confusing, but that's basically referring to drilling mud again, right? Because drilling mud is mostly oil-based, contains hydrocarbons itself. Obviously that confuses the resistivity readings a bit. So here's a series of log responses with the different depths of resistivity, deep versus shallow, for these different profiles: saline mud, fresh formation water, saline mud, high salinity, and so on. Right? So you can see different log responses let you work out which of these things you're seeing. Okay? Sounds very dull, but when you're getting down to the nitty-gritty of actually evaluating a formation, what's in it, what type of water, what type of oil and gas, this detail really matters. Resistivity logs are very useful. So here's a summary of that. Right? All that information summarised in one simple sketch, where we've basically got shale and sandstone, but each of these sandstones has got different fluid in it. This one is fining upwards. But look at the difference in the deep versus shallow resistivity logs for a gas-bearing sandstone and an oil-bearing sandstone. Right? The deep value is much higher than the low value, the shallow value, right? And there's nothing else on here that actually looks like that. Okay, so that resistivity signature, substantially bigger difference between deep and shallow here than there is when you've just got a sandstone full of salt water, you've got fresh water, right? So do you understand how a resistivity log can allow you to distinguish the presence of gas and oil in a sandstone from just the presence of water? Is that clear? You could go through the process, you could read off your deep, shallow resistivity, you could interpret the logs. And again, I'm not going to do it with you today, but I think here are some examples where you could try that out. Okay? So this is resistivity shallow, this is resistivity deep, so green versus red. Do you see a place where there's separation between the two resistivity values, deep and shallow? What about here? See, they're separated. So following the logic that we just went through on that previous slide, this, right? You look at that separation, and you look at these logs, that's telling you something about the presence of hydrocarbons in what there is as sandstone. Okay? I don't think you actually need to do this, because I think you'd forget how to do it. I think it's detail of petrophysics. I just want you to be aware that this is what you can do with these kinds of data. If you find this particularly stimulating, go and be a petrophysicist. It is pretty cool. You think you can just drop a tool down a wellbore and figure out how much hydrocarbons are present. It's quite remarkable, really. And so 2 quick look evaluations, any hydrocarbons. Check out those 2 cases and see what you think. Final slide then I think we need to go through. Remember I said about integrating log data. Here's a sort of workflow that you could follow to do this. You use the resistivity log to identify water legs and hydrocarbon columns, following the logic that we just described. You use gamma ray and neutron and density logs to identify the cleanest sands. Right? Cleanest meaning pure quartz sandstone, not arcosic, not any shale content. You use the water-bearing sand to determine the mud types of the drilling mud now that I was talking about, right? You use the increase in resistivity and the change in separation between deep and shallow logs to identify the hydrocarbon content, right? Again, following the logic we just went through in the slides. You use sonic and neutron density to check for porosity effects, gamma ray to check for shale effects, and finally, you use the caliper to make sure that you've not got it all completely wrong because your borehole is this wide and not that wide. Okay? Any questions about that? Like I said, I don't think there's much point in you doing it, but there are examples there that you can go through if you wish. I think things like seismic interpretation are your more important skills because they're things that you'll remember. Right? There is a log question on the exam, but it doesn't go into this level of detail. We'll talk more about material related to that in a couple of weeks. Any questions? Good. Well, I will see you. I'm off to Almeria on